Finish this introductory part. Gentlemen, ladies, excuse me. Look, I wouldn't like to enforce you to follow my requests, but if you don't do that, I will just will have only have the to take the action of asking you to leave the classroom. Okay, so please follow my requests. Following this introduction to language, let's talk a little bit about differential operators. Again, that differential operator could look something that is complex, that maybe you have seen sometime, that you never understood completely, but it's very simple. What is a differential operator? Well, a differential operator is just, imagine that we have some vectors, some tensors that are called field vectors or field tensor. That means that depend on the point. So we say a vector is a number, okay, three numbers, okay? But of course, if every time I move at different points of the space, so taking different values of x1, x2, x3, when I move from that point to that point, I could consider that this vector is different. That's what we call a mapping, an application. Okay? So sometimes we'll deal with vectors, first order tensors, or second order tensors, which are fields, mappings on the space, on the Euclidean space. Okay? So then it has some sense to say, well, if something depends on x, y, z, or on x1, x2, x3, what is the derivative of this something with respect to x1, or to x2, or to x3? So then we can take derivative of these entities, of these tensor entities, with respect to the space. These type of derivatives are indicated by what we call an operator. An operator which is called differential operators. So differential operators is just a way to take derivatives on tensor fields. Okay? And there are a number of them. I will mention some that we will see very commonly here. Gradient, divergence, rotation, and there are others. And all them are based on the definition of what we call a nabla operator, symbolic. According to our language, we will define all these operations in terms of an entity that engineers like, that is a way of symbolically to represent these operations, gradient, diversion, and rotation. You'll see now. Okay, so let's define something which is going to be called nabla operator, which is represented by this inverted triangle. Okay? And let's consider that this something symbolically is a vector. What means symbolically? Because it's a vector whose components are not figures, are not numbers, are just derivatives. So nabla is symbolically, that means it's not real, it's not physical, a vector whose first component is derivative with respect to x1, the first coordinate, the second component is derivative with respect to x2, and the third component is derivative with respect to x3. So symbolically, this nabla can be represented using Einstein notations as the component I times the base ai. So that's what is here. That doesn't mean that we are taking the derivative of ei. That means that this is a symbolic vector whose component 1, the one that multiplies e1, is derivative with respect to x1, component 2 is derivative with respect to x2, component 3 is derivative with respect to x3. That's what many times we put the symbol symbolically, because of course this is not a vector. The vector has to have numbers here, and instead of that it has differential operations. Okay? But using that, we can now define many useful operations on the basis of what we know, what we have seen so far, about tensorial algebra. Let's see. For instance, imagine that I have an order 0 tensor, that is a scalar, which is a field, that means a scalar field, that means that for every point x, x1, x2, x3, the space, I just have an application, a map, that returns me a figure which is a scalar. Okay? So I want to just take some derivative of that. And then the first derivative I want to take is what we call the gradient of this scalar field. What is this by definition? The gradient of the scalar field, it's a vector. It's a vector. That's the definition. A vector whose component I, the one that multiplies epsilon I, ei, sorry, is the derivative of phi with respect to xi. So it's a vector whose first derivative, the first component of this vector, that we will denote this way, gradient, so nabla, nothing, phi. Okay? Nabla, nothing in between, phi. That's what we call gradient. Okay? And it's a component which has three components, a vector who has three components. First component is the derivative of phi with respect to x1. Second component is the derivative of phi with respect to x2. Third component is the derivative of phi with respect to x3. That's the definition. Now, let's see how can we simplify this definition. Okay. Imagine that I understand that nabla is a vector and phi is a scalar. When we have a vector and a scalar, the product of them is just the open product of them. So we take the component I of the first vector times the component j, which is just one component, of the second term, which is the scalar phi. So if instead of having the nabla here, we have a vector b, the component phi times b, the component I, will be bi, the component I of b, times phi. That's what we saw. Okay? So this can be understood as the open product of the first vector times the scalar. So in that case, the open product of nabla times phi, the component I, because that's going to be a vector. Okay, so for doing that operation, I take the component nabla of I. By the way, what is the component I of nabla? We had it before. The component I of nabla is the derivative with respect to xi. So I just place it here, times phi. So far this is symbolically. So far is that symbolically. And now, beyond that point, I do the operation. So that multiplication, derivative of xi with respect to xi of phi, now I just put the real derivative of phi times xi. Okay? So in that sense, through this symbolic step that I've shown here, we can say that to take the gradient of a scalar is just doing the open, symbolically, the open product of nabla times the scalar. And then operate as if it was an open product. Okay? Look, what happens now if I want to take the gradient, but instead of a scalar field, I want to take a vector field. So now I have a vector that depends on the point. So at every point of the space, I have a different vector. Okay? A mapping that at every point returns a vector. Well, I want to take the gradient. Let's extend the concept of before. To take the gradient, what I will do? I will do the open product of the nabla times the vector, as if they were both real vectors. So how would I do that? Well, for doing that, the component ij, we know that the open product of two vectors is a second order tensor. Okay? The component ij would be the component I of the first times the component b of the second. So the component I of nabla times the component v of the second. Okay, now let's replace here. What is the component I of nabla? Derivative with respect to xi. What is the component j of v? bj. And so far it's symbolical. It's symbolic. Now let's do the operations effectively. So now I replace that by the real derivative of bj with respect to xi. So the component ij of nabla open product b, so what's called the gradient of the vector b, is a second order tensor whose component ij is derivative of vj with respect to xi. You know? So everything comes out smoothly. So finally, we can replace that intrinsically, saying, okay, then gradient of nabla, by the way, you see it here, I have forgotten the open product, because I told you that I could have put here an open product symbol, but I told you that if I want, I can just skip the symbol and put nothing. Whenever it's nothing, this stands for open product. Okay? So this could be written last as nabla open product b or nabla nothing b. That stands for the gradient of vector b. And that is a vector whose component ij is derivative of vj with respect to xi. And then I multiply by the corresponding second order basis ai, aj. Okay? So these are different ways of saying the same. To take the gradient of a vector, I just do symbolically the open product, the tensor product of nabla times the vector, and just proceed consequently. Okay? This is the way of generalizing the concept of gradient, not only to scalars, but also to vectors. And of course, we can also to extend that to second order tensors. How would I do the gradient of a second order tensor A, tensor field? That means that it depends on the space. Well, I generalize the concept. I just do the open product of the nabla open product times the tensor. Okay, that would be, look, a tensor with 3 indices, because for doing that, what I would place? The component I of the first and the component jk of the second. So there are 3 talking indices here. No one is repeated. So this is a component, is a tensor of 3 indices. That is a third order tensor. And then let's proceed. To do that, I place what is the component I of nabla, derivative with respect to xi. What is the component jk of A, ajk? So far, it's symbolic. Now let's do that differential operation. So that is the derivative of ajk. I just enter that into differential with respect to xi. So I can conclude that to obtain the differential, the gradient of a second order tensor is first a third order tensor. Okay? Second, what is its component ijk? Is the derivative with respect to xi of the component jk of the tensor, original tensor. And this is represented here in terms of components. Of course, look that this holds for I, j, k, every I, every j, every k. Okay? And this is the initial notation, and this is the compact notation. Okay? This is the compact notation. That one. Okay. So, let's talk about another operation that we can do. The divergence. I anticipate that whereas the gradient operation can be done on every tensor field, first order, second order, third order, even zero order scalars, divergence is an operation that can be only done on tensors which are of order 1 or higher. So there is no sense, the divergence of a scalar has no sense. So now let's consider a vector field like that. And let's do the divergence. So the definition that we'll do, the divergence is the symbolic dot product of nabla times the vector. Look, I put here a dot product. Okay? So that is the definition in our mind, in our language. Now let's proceed in that way. What is the in order to do the dot product, what do? I just place the component I of the first and the component I of the second. That's the definition for that product. We'll repeat the indices that are at both sides of the dot. So since there is only one index, we contract the indices. So now, what is the component I of nabla? The derivative with respect to xi. What is the component I of b? Is vi. This is symbolic. Now let's do the differentiation. Derivative of vi with respect to xy. Look, again, there is an index repeated here, I and I, a repeated index. That's in a scalar. The divergence of a vector is in a scalar because there is no mute index, no talking index in this expression. The result is in a scalar first. But look, this means a summatory. So this is derivative of b1 with respect to x1 plus derivative of b2 with respect to x2 plus the derivative of b3 with respect to x3. Don't forget that. It's the sum of the terms because repetition of indices means that we are summing for the three indices. Okay? So that's the definition of the gradient of B. The divergence of B is a scalar, because this is nothing else than a scalar, because there is no talking index that is derivative of bi with respect to xi. Well, this can be extended to higher order tensors. What about, as you will do sometimes, many times, if I want to take the divergence of a second order tensor? Well, we'll extend that concept. Imagine that I have a second order tensor A, which depends on the point, on the space. So, by definition, we define the divergence of this product, of this tensor, as the dot product, the scalar product, of nabla times this tensor. That's the definition. And now, let's see what is the final expression of that. Okay, so let's operate. First component, that's a dot product. So now I have to repeat the indices of the first and the second at the point where the dot is. So if the first component of is I, the second component, the second term would be ij. So the talking index here is j. So this is the component j. There is one talking index. So I can anticipate that the divergence of a second order tensor is a first order tensor, which is a, how do we call vector? It's a vector. Well, it has three components. Okay, how is component j? Let's see, let's proceed. It's the component I, which derivative with respect xi, times the component ij. This is symbolic. Now let's introduce that into that and take the differentials. Derivative of iaj with respect to xi. Again, this is a monomial with two repeated indexes and one talking index with j. By the way, I would like to take advantage of this moment to tell you something. What about if I change in this repeated index, instead of putting a, putting here I put k. So if I say this is equal to the derivative of a kj with respect to xk, it's the same. So the name that we give to a mute index can be any. We can call it M, B, C, L, whatever, because it doesn't pass to the other side. It doesn't affect the result. Of course, that one I matters. That one J matters because it's the talking index. Okay? So this has to be fulfilled for J equal 1, J equal 2, J equal 3. Okay? And then, in a compact manner, we'd say the divergence of I is a vector whose component J, the one that multiplies to Ej, is the derivative of Aj with respect to Xi. Okay? That's what we say. And so on. So look that, with that notation, we have just gone, now we are starting going fast, defining operations that otherwise could take a lot of time to define, to express, and so on. Okay? Well, some words here, well, that's not very important. That's what I said, that the divergence can only be performed in order 1. Another operation, the rotation, or sometimes in English it's called the curl. In Catalan or in Spanish it's called rotacional. Are you familiar with the rotational? Okay, that's what we are referring to. So let's define the rotational of a vector field. Again, it doesn't have sense for scalars. The rotation of a vector field is just the vector product, cross product of nabla times the vector. Okay? That's the definition. Okay, so let's do it. Then, for doing the dot product, we know that one way for defining the dot product is using the permutation symbol. So we said that the component I of the dot product of two vectors, which is the vector product of two vectors, is another vector. You know that one which is orthogonal to the two, following the screw rule and so on. Okay, so A epsilon ijk times the component j of that times the component k of the second. Look that again, j and k are mute indices. The only talking index is I, so that index is going to the other side. So this is hij times, what is the component j of nabla? Derivative with respect to j. What is the component k of b? bk. Now let's do the operation epsilon ijk, derivative of bk with respect to xj. Okay? So rotational of a vector b is a vector whose component I is epsilon ijk with respect to bk with respect to xj. Okay, that is very compact. That is useful because it's very compact. I can use that for other derivations. But what about if I want to take expressions of that? Well, we can prove that going back to this operation here, okay, this operation here, when I look for component 1, this, by doing this operation, aijk, it's only when I is equal 1, this term here is only different from 0 when j is equal 2 and k equal 3, or j equal 3 or k equal 2. Because otherwise, that operator will have a repeated index is 0. So in fact, here we'll have epsilon 1, 2, 3, which is 1, plus derivative of b3 with respect to x2, plus epsilon 1, 3, 2, which is minus 1, times the derivative of b3 of b2 with respect to x3. So that's what we are used to. The first component of the rotational of a vector, if derivative of bx with respect to y, by with respect to z, minus bz with respect to y. Remember that formula maybe? So that's what is saying this. But in a more compact manner. I don't need to put the three components. Using the initial notation, I can use that and specify, of course, that this holds for I equal 1 to 3. That is the specification of that. And of course, I can extend that to take the rotational, or the rotation, of a second order or third order tensor. How? Okay, if this is a second order tensor field, I just take the rotation by placing aijk, the component j of the second, and the component jk, the component kl, completely different, of the third. So this is a epsilon ijk, derivative of ikl with respect to j. This is a second order tensor, and so on. So at least we have a way to, in our grammar, to express and to deal and to work with rotationals of high order, rotation of high order tensor. That's something that we will use whenever a vector field has the rotation 0 in all points. That vector field is said to be irrotational. That's something that we use in fluid mechanics when we talk about fluids. And that means that there is no rotation in the fluid. You will see. So that's the summary. That is an example. You can do that. For that, I strongly recommend you to take this and do these operations here. For instance, just at distance. What would be the gradient, the three components of the divergence, no, of the gradient, no, the divergence of this vector, the divergence, which is the dot product, would be the gradient of the first the difference, the derivative of the first component with respect to x1, which is x2, x3, plus the derivative of the second component with respect to x2, which is the x1, plus the derivative of the third component with respect to x3, which is 0. So the divergence would be x2, x3 plus x1. Okay? Applying. And in other words, what can you do? Do the scalar product of nabla times v.